The last talk will be about Mozzarella, efficient Vector-OLE and zero-knowledge proof over the Detour to the K. And the work is by Carsten Baum, Baum, Alexander Hansen, and Peter Shaw. And Carsten is giving the talk.
Okay, thanks, Luisa. Just before I start, also concerning the rump session, because somebody has asked which talks will be accepted at the rump session. So we were so gentle to accept all the submissions from you, but in a randomly permuted order. I can prove to you that it's all the talks in random permuted order using the techniques from the previous speaker, if I so would. Anyways, this talk is going to be about efficient Vector-OLE and your knowledge proofs modulo 2 to the K. And it has the fantastic title Mozzarella for questionable reasons. And so you've seen these CITIC t-shirts, and some people of you might ask what CITIC has to do with us and Aarhus. And actually, what people don't know is that CITIC was the foundation also to this line of work, out of which Mozzarella sprang, because already back in the days, they were smart enough to make CITIC the abbreviation for cheese terminology and cryptography. But okay, let's be serious here. So what I'm going to talk about is zero knowledge proofs modulo 2 to the K, which means that your statement is defined modulo 2 to the K, and you want to prove something about a circuit or so that is expressed this way, right? So how could you do this using the techniques that are around today? Well, either so the straightforward approach, which has been taken most of the time, which is to emulate this mod 2 to the K arithmetic modulo some prime p, right? You just choose a p that is a lot larger than 2 to the K, and now you emulate the arithmetic modulo p using integer arithmetic. Now the problem is that you also have to prove modular reductions after you have done an operation, right? So this is going to be quite expensive to do this emulation. And also you can't, so a lot of zero knowledge proofs, for example, give you free linear operations, right? So if you have two values that you have stored in some circuit, then you can have you can easily prove statements about, let's say, the sum of these two values, right? You can't do that as easily in this case, because you could have overflow and these kind of things. So if you want to prove statements about something modulo 2 to the K, you usually want to use the fun stuff that operations over 2 to the K have, like bit fiddling, shifting stuff around, and you can't have that. If you emulate the arithmetic modulo P, you can't have that for free. Next up, in another approach that was, for example, taken in a paper called Mystique by Wang et al., is to emulate this arithmetic in this integer ring by just storing all these bits individually, and then proving statements about vectors of bits, right? So you can obviously do mod 2 to the K arithmetic by decomposing this into K bits and then proving statements about vectors of bits, right? Now maybe you can do, you could do that, and now you can easily access the individual bits of these values. Has the disadvantage, again, you can't do free linear operations, right? If you wanted to add two numbers together, you would now have to prove in zero knowledge that two numbers add to a third number, because if you do additions of integers, that involves AND gates as well, right? So this again doesn't go for free. So we thought we should do something about that, and in a work that appeared at last year's CCS, together with Alex, Peter, and Leonard, who were also co-authors in this paper, and Benoit Razé from Galois, we built a zero knowledge proof system that works natively over rings mod 2 to the K. It just has the teeny tiny disadvantage that for that we would have to have so-called Vector-OLEs. You have heard about Vector-OLEs earlier today from Lisa, for example, and these Vector-OLEs have to be defined over this ring modulo 2 to the K. And well, at the time of writing, nobody had any idea how to do this efficiently. So, well, you know, we had a cool online phase, but not really an efficient offline phase, as it so happens often in MPC. And so we thought, well, that is not great. What can we do? Thus, Mozzarella. Mozzarella is a efficient Vector-OLE extension protocol that uses techniques from, for example, Wolverine. To build this, we need a different type of LPN assumption. I'll tell you in a bit what this is all about. We also, and to stay within the cheese references, have built a new designated verifier proof protocol, which we call Quarksilver. And it is the first that uses these efficient multiplication check techniques that were introduced last year by Detour et al., but adapted to modulo 2 to the k, which is a pain, but luckily we've done that. So now it's done. Now we're happy. And also we implemented this thing. So we didn't just think about cheese. We also made cheese. And what can we do? We can do 100 million pseudo-random vector-OLEs modulo 2 to the 144, which can give you proofs modulo 2 to the 64, if I'm right. Maybe I'm right. Alex says I'm right. Fantastic. In around 50 seconds. And then you can prove, like using these vector-OLEs, you can prove more than 1 million multiplications over that ring per second. So it's not as fast as it does over fields yet, but we'll see where we can get. Okay. Well, I think I don't have to introduce zero knowledge proofs. This is the zero knowledge session. It's the third talk in the zero knowledge session, and you all want to go to the rump session, so let's skip that. Or you want to have dinner, I don't know, first dinner, then rump session. So what I need to explain to you is, unfortunately, the committed proof paradigm, or fortunately, this is how our zero knowledge proof system works. This was, if I remember correctly, introduced by Ivan and Ronald back in '98. Or maybe before that. I'll see based on the reaction from Ivan. Ivan doesn't know. That's good. Sorry? Too long ago. Okay. So what do you do? First of all, you express your statement that you want to prove as a circuit, right? You can always do that. So in this case, for example, we have this beautiful circuit up here, right? That has some addition gates, multiplication gates, whatever. And so what do you say? Well, if my circuit outputs 0, then the statement is true, otherwise not, right? So so how do you prove things now? Well, here it's over field F for now, because back in the days people used fields. Now we can do rings. Okay, so how do you now prove something about a, let's say, an input to a circuit that you know that makes the circuit evaluate to 0? Well, the prover first of all makes commitments. It commits to the input wire, so it commits to the witness that is going to be fed into the circuit, as well as all the intermediate values that show up when you evaluate the circuit, and then it also commits to the output of the circuit, right? I guess you've all seen that before. So here's the circuit, here's the data, oops, commitments. Okay, cool. So now they're hidden. What is the prover going to do next? Well, first of all, it's going to open the output commitment, right, which hopefully is 0, because otherwise your evaluation is not really proving the right statement. So it's going to do that, but it doesn't give you any actual information if the proof did the right thing. So in addition, the prover is also going to show in zero knowledge that the output commitments of each gate are consistent with the input commitments of each gate, right? So this fantastic proof technique shows that using commitment, you can reduce zero knowledge to zero knowledge. That didn't really help much. But of course, you've all noticed that this is any arbitrary circuit, and you reduce this to zero knowledge proofs to two types of zero knowledge proofs. One is show that a commitment contains the sum of the values inside two commitments, and the other one is a commitment contains the product of the values that are in there, right? So we kind of decomposed zero knowledge into two simple elements. Now, once we have a commitment scheme with a zero knowledge proof for this, we have a zero knowledge proof for arbitrary circuits, right? This is kind of how you do it for garbled circuits. Okay, and also what was observed back then already, I just want to remind you, if you have a linearly homomorphic commitment scheme, then this all works quite neatly, because you can just, well, you get the addition gates for free, right? You just, if you have a linear operation for your gate, you just add the commitments together and there you go. And if you want to prove multiplications, well, you use Beaver's circuit randomization technique by, I don't know, committing to a random multiplication triple and then opening the difference, yada, yada. You have all seen this again and again and again. And it's actually the approach that we've also been taking in our work that's from last year. Anyways, so now we all know how to build zero knowledge proofs. Now we just need the commitments, and then we're fine, right? So how do we build these commitments? And as a setup, we use Vector-OLEs over rings. So what is happening here? For Vector-OLE, we have a sender and a receiver. It's just a recap on what you've seen essentially earlier today and before that too. And we have the sender here on the left side, the receiver on the right side, and it's going to be the sender that will later on be the prover, and the receiver will be the verifier. But let's stick with standard terminology here. So the verifier is going to input a value delta, and this is from a subring. So here we are over 2 to the L, where our vector is defined over, but delta is defined for some 2 to the S, where S is smaller than L. Okay, so just a smaller number. And then our Vector-OLE on input W and M from the sender is going to compute this relation here and output it to the receiver. Okay, it's just a box that you put delta in, and on the other side you put W and M in, and out comes this correlation. That's actually only an OLE, but if these things here would be vectors of values, then you get a lot of correlations where you always use the same delta, Vector-OLE. Yeah, good, that's what I just said. And then there's also something called random Vector-OLE, which is what we usually use in these proof systems, namely that this magic box here is going to choose W and M itself, and it's actually going to output it to the sender. So instead of the sender inputting this, the arrows just turn around and they come to the sender magically. And in previous works, based on this fantastic homomorphic sequentiary techniques, there was a lot of works that showed how to realize this for correlations modulo 2, which would be OTs, or for primes P, for arbitrary primes, which then is OLE or Vector-OLE. Okay, so far so good. And then once you have these Vector-OLEs, you can easily build linearly homomorphic commitments. Again, this is nothing too surprising. How would this work? So we're going to construct information theoretic MAC, which is then the same as a linearly homomorphic commitment. So let's say we have a random Vector-OLE here, right? So we have that the verifier has this value K and this W, and the prover, no, the verifier has delta and K, and the prover has W and M. And you can look at this as a information theoretic MAC on W modulo 2 to the K. So now we're going to squeeze a K in between everything. So just so you can see this, we have an S, we have K, and we have L. And what we show is that this thing up here is an information theoretic MAC on W modulo 2 to the K, which I'm just going to denote as W tilde, using the key delta and M. And this again is linearly homomorphic, right? If you have two of these things with this different values, W1 and W2, and you add them, well, you have the same delta. So you can just put them together, everything is fine working as you would expect it. So linearly homomorphic commitment scheme, I'm not going to say now why it works. Only thing that is a bit surprising is when you open it, as I said, you actually don't get a binding on the value W, which itself is from 2 to the L, but you only get it to be binding on W tilde, which is W modulo 2 to the K, so something smaller. You have to cope with this in the zero knowledge proof system, but for now, let's ignore this. It later has an impact on parameters, but parameters, who really needs them anyway? Anyways, the important part here is that if you pick L to be larger than K plus S, then we have that this is binding the prover to a W tilde, except with probability 2 to the minus S. So that's cheating probability. Pick S to be 40 and be happy, right? Don't do Fiat Shamir on this, as Yehuda told us, right? Then we're in deep trouble. Anyways, so now these are homomorphic. So the code name for this project was cheese rings, because this is rings and we do cheese. So I had to keep this here. So now that we have Vector-OLEs, we have these commitments, and I explained to you that we now have a knowledge proof, right? Using just standard techniques, so we're done. But I still have a bit of time. Also, the food is not yet ready at the math canteen, I heard, so I'll just keep talking. For now, we still assume that the Vector-OLEs come from somewhere, right? So now, how do we make them? And so there are two ways of doing this, right? One solution, which is what we assumed, is that you just make all these nice correlations from scratch. That is going to be expensive because the tools for that we have right now at our disposal are not going to be that efficient. Or you do, as Lisa has told you earlier today, and I'll just depict beautifully here on the slide, you start with a bit of correlation, and then you expand your bit of mozzarella into a lot of mozzarella, right? So you get from a bit of cheese to a lot of cheese. I'm sure that Swiss and Italian people would find such a tool fantastic if it existed in the real world. Anyway, so sorry. No, it's just it's magic, right? Anyways, so this is actually the path that we're taking, right? So we start with a small amount of Vector-OLEs, and we expand this into a lot of Vector-OLEs, and then you can just amortize over time, right? So initially you have to compute all of these, or a lot of this. You have to make a bit of mozzarella. That might cost you something, but then you just repeat it again and again and again and again, and then you can forget about what has happened before. Okay, and how does this work? Just a quick reminder, if you were asleep before or after, before lunch, that's so what was this, the primal LPN problem, which is what we're using here, right? So in LPN, you have a short secret. In our case now, defined modulo as a number modulo 2 to the k, or actually 2 to the l, so set k equals l. Anyway, you have a short random vector here. You multiply this with a large expanding matrix. For example, the generating matrix for a code, but here there are not so many codes maybe that we have. And then you add to that the sparse vector e, and then you hope that this, or you get that this is computationally indistinguishable from a long vector x that is uniformly random. So you expand something short into something short and random into something long and random, or pseudo-randomly long and random. Right, and the nice thing is, so this here is uniform, this thing is now uniform, and all you pay for this is a bit of sparse randomness that you have to generate as well. Right? Okay, cool. And again, so how does this work? You have this short secret, and you multiply it with the matrix, and you add something, and now you've all probably been thinking that right, so okay, what you've all been thinking, I get there later. We now want to do this a bit different. Generating a uniformly random noise can be a bit painful, so what we use is actually a slightly different version of that, where instead of having a regular error vector with noise everywhere, we now have kind of a structured error vector where you have a block of entries here, and there's one error in each of these blocks. It has an impact later on if you do the security analysis, but overall you hope that this still gives you something that is somewhat safe. This also has been used in previous work, so we're not the first ones to suggest that structuring the noise in these LPN instances is going to be is something that you should do. Anyways, so as I said, this is a regular assumption that's well established for F2 and FP, right? And there's lots of cryptanalysis that is available for this, right? And our hope, finger crossed, is that that LPN modulo 2 to the k might be as secure as the stuff modulo some prime, as the attacks seem to work like before. At least it was our hope when we wrote the paper. It later on turned out in a recent work that just appeared on ePrint that this is not quite true. There are special attacks that work only over rings modulo 2 to the k that make attacks faster there, but we think that we can choose the error distribution in a clever way to circumvent these attacks, as it always goes, right? You have some idea, somebody breaks it, you tweak the parameters, there you go. Nacho shakes his head, so probably it's not going to be secure ever. But then Nacho is always a bit pessimistic, so yes.
If you go one slide back, there's one technical question.
Yes, this or
one back, one slide back there.
Yeah.
If the noise you add is always yellow, doesn't that make it super easy to find the?
I haven't thought of that.
I think this could be the source of the attack.
Yeah. I'll Alex, when you give the talk at crypto, I don't know. Alex, when you give the talk about this at crypto, please paint them green or so. I don't want to have the same question again. Okay, fantastic. Thank you. Anyways, I think Jesper's up to something here. Okay, so as I said, this stuff is the commitments or the Vector-OLEs are closed under linear operations, right? So an LPN is just multiplying a short secret with a expanding matrix and adding something is a linear operation. So we do what you expect people would do. We have our secret here or random Vector-OLEs. We multiply it with this matrix A, and then we have vectors of Vector-OLEs where there's only one that is non-zero. We add this and we get a long pseudo-random Vector-OLE vector, and we would be happy because from that we can now build all our zero-knowledge groups, right? So I'm already seeing that I run a lot over time. How you now how you do this? You've seen this essentially earlier today, so I'm not going to go into detail here. All I'm saying is that if you want to compile previous techniques that achieve this generation of these like one-hot vectors, if you adapt them to the setting modulo 2 to the k, and you want active security, and for zero-knowledge proofs you want active security because your prover might be malicious, then you have to do two things. You have to make two tweaks to the protocol to make stuff actually work. And actually, we built something into a protocol that defends against active attacks. Unfortunately, this leads to some leakage on the secret, and we then actually show what the leakage actually is that you have in the protocol, and show how it turns to leakage into the LPN setting, and then we adjust the LPN parameters to cope for the leakage there. Anyways, so now I'm like semi 2/3, 3/4 done. What I also want to say is that we could use the multiplication techniques that we had in previous works, but they would be somewhat inefficient. So instead, we adopt techniques from another work called Quicksilver to work in our setting, getting us to what we call the Quadsilver protocol. And just on a high note, how it works by saying, well, if you have three Vector-OLEs such that the secrets are multiplicatively correlated, then you can actually write a new Vector-OLE correlation that is as before between the prover and the verifier. And now you just check this new correlation. This was observed in this previous work called Quicksilver. And this is secure as long as the prover cannot find delta. So you can again reduce this to the same security that you have for your commitment scheme. Again, this doesn't simply carry over to the setting modulo 2 to the k, because before that it was about that delta has to be a root of a random polynomial. Delta has to be the root of a polynomial that the prover defines, and the prover doesn't know delta. Now, modulo 2 to the k, there are lots of roots that a polynomial of degree 2 can have. So we had to work a bit to make this work. And we also found a way of extending this multiplication check from checking one multiplication at a time to checking a lot of multiplications at a time. This again is a lot of boring math that once the paper is on ePrint, you can check there. Anyways, last but not least, I know I still have a bit of time. I just want to So I want to mention that we're not just doing cheese in theory, we're also doing cheese in practice. So this is I think this is the so-called Cooper's Hill cheese rolling contest, which is a cheese run, and we actually got our cheese to run. So this is an event that happens every year in the United Kingdom, where people run after a cheese that rolls down a hill. I just found it interesting. Never mind. Anyways, our Vector-OLE, as promised, if you set the ring to be 2 to the 144, then you can have 170. I think this should be generating 1 million or 10 million, 10 to the 7, 10 million? 10 million Vector-OLEs with 40 bits of statistical security. And to do that, we need 178 nanoseconds per Vector-OLE. That gets you to the 50 seconds for 100 million that I mentioned, I think, I hope. And just to mention, if you have a comparable setting as Wolverine, which you would use to prove statements modulo 2 to this around 2 to the 64, they are quite a bit faster than we are. And then for Quarksilver, we have also implemented the multiplication check, and there we have that it takes per checked multiplication these many nanoseconds if we amortize over 10 million multiplications. Okay. Just to summarize quickly, so what we built is, what I showed to you was, well, Vector-OLE modulo some 2 to the L gives you homomorphic commitments modulo 2 to the K for a K somewhat smaller than your L. And then once you have a few Vector-OLEs modulo 2 to the L, you can extend them to a lot of Vector-OLEs modulo 2 to the L based on the LPN assumption. Also, what I showed, or couldn't really show, but never mind, is that you can do efficient multiplication checks for Vector-OLE values in zero knowledge based on techniques that we introduced in this work. And also, we've implemented this, and if I would have looked at the slides that I made there earlier, then I could have explained to you a bit more on the implementation details. But if you want to know something about that, the paper is soon going to be on ePrint, or find Alex, who's sitting there, and he might tell you a lot about what has been happening in the implementation. With this, I'd like to thank you. See you. Ivan.
One comment. I just got my act together. So it's true that protocol you showed was first time in that paper from '98.
Okay.
In fairness, the ideas to trace back to Prasad Shamikapur in '86 or '87.
Yeah, I mean, I think yes, but I think for homomorphic commitments, you were the first to use that, right? Yeah. I mean, without the homomorphism that was around before, yes. More questions or comments hidden as a question? No? Jesper?
Sorry, this one is serious.
Oh,
So
oh Lord.
Slide 6. Will you go back? I'm sorry, that's gonna take.
Yeah.
Oh,
Nah.
this one is to end on time.
Ah, okay, good. Yeah. You really wanted to know slide 6?
Yeah.
They
went a bit fast here. I didn't get it. But what's that?
I think you should attend this cryptographic protocol theory course that is I think running the next term here at Aarhus University. You might even be familiar with one of the instructors.
Yeah, sounds really cool.